Thank you for the introduction. For those of you that don't know me, my name is Taku, as you just heard in the introduction. And I am an oil and gas guy, and I also am in the world of finances. And then so I got probably 2 strikes against me. Some of you might be wondering what a guy like me is doing at a conference like this. I was asked to give this talk because just the nature of my business, I have to oftentimes evaluate a lot of different technologies. And one of the things, the hot topics that's being discussed right now is these unconventional plays, these shale plays. And I'm sure, as you are all aware, there's been a lot of media about, well, what happens if you drill these wells and you have a lot of methane emissions? Is that bad for the environment, et cetera, et cetera? So my job is to sort of give you some cocktail numbers. And this is not a very heavy-duty talk, so you can relax. This is just, if you can take away some cocktail numbers, that'd be great. What I wanted to do was to sort of frame this whole methane emissions from unconventional plays in the larger context of greenhouse gas emissions in the first place. There's been a lot of papers out, people are raising alarms, and I just want to make sure that we all understand where it all fits. So this is just a GWP for 20 years and 100 years, and this is just a very rough estimation. But you can see the red pie is where the methane occupies on the 20-year scale and a 100-year scale. So of this methane that comprised of the GWP, what I did was I took the CH4 emissions from unconventional wells and in the US annual. And I said, okay, well, of the methane in the previous slide, how much of it comes from well completions? As it turns out, it's not a whole heck of a big deal. It is still 3%. The rest of the natural gas emissions comes from natural gas systems, and what's comprised in the natural gas systems is pipeline leakages, equipment leakages. Those are 28% in the US, 28% of the methane emissions comes from those systems, and everything else, including agriculture, et cetera, comprises 69%. So just to put the CH4 things into perspective as to why people might be making a big deal, emissions from unconventional wells, it's estimated to be about 48 billion cubic feet. Now that's based on EPA estimates. And if you don't believe the EPA, now if you're an oil guy or a gas guy, you say, no, the EPA numbers are too high. So divide that number by 2. And if you're an environmentalist, they're saying, no, that number's wrong. Well, multiply it by 5. And you still will come out to roughly, in the large scheme of things, the whole natural gas systems emits 10 times as much. And the CH4 sources in the US is even greater than that. So even if you were to divide it by 2, multiply by 5, you're not going to get a whole significant change in terms of the impact of well completions on methane emissions. In CO2 equivalent terms, it's about 19 teragrams, or 0.3% of the GWP on a 100-year scale, or 50 teragrams, or 0.6% of the GWP on a 20-year scale. So again, fairly small numbers if you look at it this way. Revenue loss, now this is where oil and gas companies get a little bit sensitive. It's in their best interest, actually, to capture these things. It's about $200 million a year if you just let this all go. So one could argue that it's against the oil and gas's industry's objective to just let this methane go. And that's one of the reasons why the oil and gas industry as a whole think that there's a whole heck of a lot less than the 48 billion cubic feet that EPA has published. In a fraction of net annual natural gas demand, we use about, in the US, 21 teracubic feet per year. So 48 billion cubic feet amounts to about 0.2%. So just because it's small doesn't mean that we don't have to be worried about it. But what I did here was just based on this simple calculation of, this is from the EIA, this is the energy production growth from 2010 all the way up to 2035. And I said, okay, well, the top purple part is the CH4 production. And I said, all right, let's just assume that the CH4 production, the entire growth, comes from unconventional wells. So let's just apply that growth factor, and let's use all the numbers from the previous slide. You're still not going to get a whole heck of a lot of difference. So the bottom line here says 60 billion cubic feet a year, or $240 million per year loss of methane due to CH4 productions from well completions, even if the CH4 growth path is what EIA presented to us. Now, again, this is strictly for the US. So one of the things that we need to worry about is that with this growth of tapping into unconventional plays, there will be developments in China and developments in India that we have to worry about, and they may not be as regulated as the US. So reducing impacts from unconventional plays, what I did was, even though it's a small number, there are ways to reduce this number. This seems to be the lowest hanging fruit in terms of in the whole production cycle of the methane. There's pipeline leakage, but those are often hard to detect, and they're hard to survey. And believe me, they're hard to survey because I'm out there in the field, and it's hard to locate a lot of the leakages. Equipment leakages are small, and they are dispersed over many, many locations, and accounting is an issue. So when it comes down to it, if you look at the whole unconventional play cycle, where you can make the quickest fix is when it's being drilled, right? So the rest of the talk will kind of focus on the following points. And again, this is to give you an idea for those of you that will read in the newspapers, oh, this fracking, methane from fracking. Now you'll know exactly when and how this methane is released from the earth. And so when do emissions occur? That's the first one. And EPA has now instituted that everyone go with this thing called a green completion. So then I'll talk about what the heck a green completion is, what technologies are available to execute EPA's goals, and then I think the important parts are why is this sometimes hard to implement green completions, and then I'll end with academic opportunities. And I think this is where GCEP could have some impact, just because there are some academic endeavors that will help minimize some of the wells that are being drilled unnecessarily. So when does this methane occur? For those of you that are not familiar with the actual fracking, what happens is you drill a vertical, and then there's a bunch of shale plays. Some of them are small, some of them are dispersed. And what you do is you turn the well bore, or the drill bit, and the drill bit goes sideways horizontally for about maybe 5,000 to 6,000 feet. The entire fracking doesn't happen at once. It happens in stages, in about 5 to 6 stages, so about 1,000 foot per stage. So what happens is, at 1,000-foot intervals, they will first frack the first 1,000, right? So they pump in that fluid. The rocks get shattered. They splinter into directions that they want to splinter in. And all the water comes rushing up the wellbore. And along with this fluid frack water that you hear about a lot, the methane that's been liberated also comes back up to the surface. Some of the wells, they just let it go. It just goes into an open pit. So you have water with dissolved methane with some free methane. It just comes to the surface, gets dumped into the pit, and pit is allowed to evaporate. Now, after the first stage is done, they set a plug to isolate the first stage, and then they go with the second stage. Isolate that, go with the third stage. So this is what it looks like sequentially. So you have a plug that isolates the second stage and the first stage. So the second stage gets closer and closer to the second stage, third stage. It gets closer to the vertical part of the wellbore. And then once all of the zones have been fracked, what happens is they have this thing called a drill out. So all these plugs are impeding the way of the flow. So there's, let's say, 4 plugs in the wellbore. They got to go in there and drill out these plugs. When they drill out these plugs, they let the methane just kind of rush up as the plugs are being drilled out. And this methane is sometimes not captured. Then the final stage of the well cleanup is the last stage where you can get more methane seeps or methane flowbacks. So what happens is you pumped in a lot of fluid into the subsurface. And oil and gas guys don't want that fluid in the wellbore. And this is not well understood as to why the fluid has to leave the wellbore so fast. People have different views as to how the oil is trapped in the shale. In any case, the industry standard is that you want that fluid, once it's been pumped in there, you want that thing out fast. And so in order to encourage that fast exit of the fluids, what you do is you pump in nitrogen and CO2 or water or whatever, or vapor, sorry, and you just try to help that water column out. And when you do, there's always free methane, and you just sometimes let it go, as you can see in this figure here out in the field. So EPA said, okay, well, we really ought to capture this. And when this EPA green completions things came out, methane really wasn't the target. It was really more the other volatile organic compounds. The fact that methane is now regulated under this green completions regulation was just a nice bonus. Green completions are mandatory starting January 1st, 2015. Until then, all production gases must be flared. And the idea there is that by flaring it, you're converting methane to CO2, and therefore, on shorter time scales, it's just better for the environment. Colorado and Wyoming are the two states that already require green completions. And however, operators in Colorado are given quite a bit of leeway from the GCEP, which is the governing state body. In case methane can't be captured for safety reasons, and that safety reason is loosely defined, they can flare it or just let it go. So this is a picture of how the green completions work, as instead of letting all that stuff go into the atmosphere, if this is the wellhead over here, goes into a thing called a sand trap, because a lot of the fluids that were used to frack the well required a lot of sand and other proppants. The sand and the gas get separated, and then the gas goes into the market. And this is what it looks like in the field. So are there green completion technologies already available? The answer is yes. These three companies, BP, Weatherford, and Devon, these are some of the leaders in the industry in terms of providing that system. It's readily available. It's not very cost intensive. In fact, you can make back a lot of your costs in about 3 months if your well productions are high. And in case you can't capture the methane, you have Canadian companies like Quester, who is in the business of flaring these gases. So the question becomes, well, if all of these things are available, why is it not being done? There are 4 main reasons as to why some of these things are difficult. The first thing is safety. So some reservoirs have high pressures. And flowback units, so when you have the flowback unit, instead of, if you were to dump it into an open pit, if you have to put it through a sand separator, et cetera, you have basically more piping and more equipment. So you subject that to high pressures, high reservoir pressures, and these washouts could happen. And these are just for the safety of the personnel at the surface. A lot of the companies choose not to participate in the green completions today. Another challenge is the opposite of a high pressure reservoir. So when you have low energy reservoirs, when you have a low energy reservoir, the reservoir can't, so you pump in the fluid and the reservoir doesn't have enough pressure to send the fluid out, back to the surface. So instead, in these situations, what people do is they inject air to clean out the liquids. And when you, as you can imagine, when you inject air or nitrogen or CO2 to clean out the liquids, you now have to separate out gas. So you have to try to separate out CH4 from the air and the CO2 and the N2, and becomes prohibitively cost ineffective. So therefore, EPA actually grants these low energy reservoirs to not fall under that category of green completion requirements. The third one is wildcatting. So if there's no sales line, no matter how much methane you capture, you can't sell it anywhere. So EPA basically says, well, if you're in a wildcat status, then go ahead, you can flare it or just let it all go. And by nature of these unconventional plays, they're unconventional and they're risky because it hasn't been tapped before. And there's no sales line because people think it's risky. And so now you're in this place where you're trying to regulate methane leakages, but you're saying, well, wildcat wells are okay. And a lot of these wells where you have these methane leakages are happening at the wildcat stages. So, you're kind of defeating the purpose. And then lastly, the impurities, just very quickly. As I said, during well blowdowns, et cetera, or the gas can contain impurities that make it very hard to separate out just the gases. So you can do sand and gas fairly easily. But when you have to separate out gas from gas, then it becomes not very cost competitive. So academic opportunities, just to wrap up. So what if you can't capture CH4, and what if you can't flare the flowback gases because the impurities are too high? Well, the academic opportunities that exist will help limit the number of wells that are drilled unnecessarily, and there's tons of that in the industry today. If you look at the EPA reports and look at how many wells were actually drilled, flowed initially, and then were deemed non-productive because the decline curve dies really quickly, you look at a 6 in 10 success rate. So 5 of the wells are just useless even after initial flowback of the methane. So I developed these 3 points with a professor at Texas A&M, Professor Blassingame. And he feels that the 3 opportunities are developing an understanding of flow physics in the subsurface to have better decline curve estimates, improve reservoir characterizations and simulation techniques, and then using those 2 points to engineer enhanced oil and gas recovery methods from these unconventional plays. So in conclusion, CH4 impact from unconventional natural gas well completions are relatively small in comparison to other greenhouse gas emission sources in the US. CH4 emitted annually during unconventional well completion accounts for 3% of all yearly CH4 emissions in the US. Does not mean that we should be careless with it. It just means that this is the 3% that's a very low-hanging fruit that we can probably improve. CH4 emissions during an unconventional well completion occur during frac fluid flowback, drill out of plugs, and then clean out or the blowdown of well bores. Cost-effective industry solution is readily available. However, there are implementation challenges when the reservoir pressures are high or too low, or the wells are located far away from sales lines, or you have high impurities. And again, the next best thing after CH4 capture and flaring is to basically minimize the number of wells drilled in the first place where the academic opportunities lie. So with that, I'd like to end my talk, and I'll take your questions.
Okay, questions? Yeah? Yeah, go ahead.
Joris Cornet from Ecovis. I have a question. I'm certainly not a reservoir engineer, but the 3 points you mentioned for new research for this topic. Mm-hmm. So improving the simulation, sure, reservoir characterization, and EOR methods. Yeah. Can you draw perhaps a link between CO2 storage and would these topics, if you address these for, in this case, CH4 leakage, mm-hmm, would they also benefit for CO2 injection maybe?
Well, I think looking at enhancing any reservoir characterization, like Dr. Benson was just saying, a lot of the success of the CO2 CCS projects hinge upon good geological characterizations. And this is true in a lot of the techniques that you would end up using for geological characterizations for CCS, you would end up using for these as well. Geological characterization in shale plays become really important when you want to orient your wellbore. So you can imagine if there was a play here, and a play here, you want to make sure your horizontal well kind of goes through all the plays. Now, sometimes in the industry, the well goes that way and you miss the 3, right? So I would say geological characterization has the biggest impact in terms of being able to share a lot of the technology with plays like CCS. Yeah.
Another area of research might be better understanding of the and control of the fracking process and
Sure.
improvements on that.
Sure.
And one of the complaints of the oil and gas industry about that is that they don't want to reveal any of their proprietary processes
Sure.
and fluids,
Right.
which is perhaps an impediment to that understanding.
Right. And I think you're right. I mean, completion processes are huge. I've been out on well sites now where, so for example, if there was a shale play here, a shale play here, and a shale play here, and they're separated by small lenses of sandstones, it would be nice if they can take a well bore and then you frack all 3 zones at once. But they're not entirely sure if they can achieve that. And then so if they don't achieve it, what they end up doing is they drill this, produce out of that, and then they got to go through to the second shale layer, produce out of that, and then the third shale layer. So if you can minimize it by fracking through the whole thing in the first place, I mean, you're right. I mean, those are opportunities. If people understood the fracking process is a lot better, then it's in the early stages. Those things are in the early stages for sure. So data is being collected though. So in that case, you frack it, and then you use that energy, the acoustic energy, as a way to seismically image the subsurface. And people are trying to determine how far the fractures go in the subsurface and if they can control that using different fracking techniques and proppants and fluids.
How about back there? Yeah.
Would you care to comment on the reaction of the people who are doing this to the Deutsch Committee report?
I'm sorry, I'm not aware of the Deutsch Committee
Well,
report.
there's been a fairly careful study done on the environmental risks and the consumer risks to those procedures in a committee chaired by John Deutsch at MIT and participated in by a couple of people here, including Mark Zoback.
Right.
Some have objected to it. Some obviously think it's a worthwhile sense of hesitancy. What do you think about it?
Well, I think aside from this talk, right, just fracking in general, natural gas, tapping into these unconventional plays, here's where I see the danger, being out in the industry. The Schlumbergers, the Halliburtons, the big names, I think when I talk to them out in the field and when I watch them work, they're careful. They do what they're supposed to do. They do the engineering. What concerns me is this growth and this craze into the Bakkens and the Haynesvilles and all this. And when I go to those sites, you don't know who these drillers are. You don't know who these frackers are. They're there because the money's there. And they're not, I would say that those are the dangers when you end up completing wells or fracking wells by those guys because of the craze, and it's not very well regulated. That's when a lot of these things could occur, the risks to consumers, both the consumers and to the producers.
Okay, we'll take one more question, and then we've really got to wrap up, and it's got to be a quick answer.
Okay, sorry.
Thanks. Oh, okay, over there. Excellent.
Hi. So first of all, I really appreciate your talk. I don't know very much about natural gas fracking, but when I think about the climate impacts of unconventional gas resources, I think about the numbers in a different way than the way you've presented it. You presented 3% of total emissions of CH4 or methane coming from these unconventional wellheads. And when I think about it as a percentage of the produced natural gas from the
Sure.
unconventional plays.
Sure.
And so can you comment on that?
Yeah, and in fact, when you look at the Howarth paper that came out from Cornell, he states a 1.9% of the whole lifetime of the well. And if you actually follow through with those numbers and convert it to the way I presented it, multiply this 48 by, I don't know, it came out to be about 160. So that's why I said, I was joking, it was a multiply by 5 divided by 2. So in the larger context, you're right. I mean, and what concerns me again is the growth of this industry, right? So.
Okay, well, sorry, I think we need to wrap up. Okay, well, thank you very much, Taku.